Hello and welcome to the next video on my series on system software. Today we're going to be looking at memory management. So let's start with some basic points. Computer memory is a limited resource. One of the key jobs of an operating system is to manage this memory. Memory stores the programs and data in use by the system. Memory management allows multiple programs, or more technically correct processes, to be stored in memory safely and efficiently. Memory management protects programs/data from each other. Each different program will be using its own data. Without memory management, one program could change the data of another. It would also be possible for a maliciously coded program to access or amend the data of another program. And actually, believe it or not, this is something that used to happen quite a lot. Older operating systems, for example, earlier versions of Windows and other similar systems, programs are very much trusted. It was very easy to write a program that, because of bad programming or malicious intent, could overwrite or access the data of other programs. And this could cause freezes, crashing, made hacking easier, caused all kinds of difficulty. The memory management aspect of operating systems restricts each program to accessing and amending its own area of data. So that prevents those sort of problems from occurring. Sometimes, however, two programs may have a valid need to share data. Again, it is the operating system memory management that allows this. So think of a simple example. You've got some data in Excel and you want to put it in your Word document. You can get that data into Word quite easily because of the memory management facility. It allows you to transfer information between those two running programs. Memory management also allows programs to use more memory, more RAM, than the system actually has. And that's what we call virtual memory. You might be familiar with this from GCSE, but we will go through it again in a little bit of detail. The different types of memory in the system must be used properly so that each process can run most effectively. So here we've got a kind of abstract overview of how memory works on a typical system. And the idea is you want to keep the data and instructions that you're going to use most often or in the near future further up here towards the CPU, and the data instructions that you aren't going to need for a long time further down. And just while your computer is running, it's constantly transferring between your disk storage and your RAM, or back again, between RAM and cache and back again, between the cache and the CPU, and just backwards and forwards all the time. When an operating system manages computer's memory, there are two broad tasks that need to be accomplished. Each process must have enough memory in which to execute. Additionally, it can neither run into the memory space of another process, nor be run into by another process. How then is memory divided between processes? Well, let's assume that all the programs we store are stored continuously, one after the other, as they are loaded into memory. So now we have program A, program B, and program C all running with a little bit of free space left over. But let's imagine application B is closed. So then we've got an extra part of free space. We've got some free space here, some free space here, and we've still got program A and program C running. If a new application is started, then how do we fit D into RAM? So you can see here, there's not enough space here or here to run it, so I can't just put it in here, and I can't just put it in here. It's too big just to slot into any of those two free spaces. So what do we do? Well, one thing students often suggest is that we could shuffle C along so it starts immediately after A, leaving all this free space together. So as you can see there, we just move C along, and then we'd have a nice big bit of free space at the end where we could add application D into the RAM. But while this is possible, it's inefficient, as having to constantly rearrange programs in memory in this way would have a negative effect on system performance. I mean, think about how many applications, how many processes, how many things are running all the time on your computer. Even if you don't think you're running very much, go into the Task Manager, have a look at all the running processes, and you could see this would take a lot of work if we tried to use this system. A better solution is to split programs up. So in the example above, we could have part of D in this free bit of space and part of D in this free bit of space. Now this is how we actually do it, but the big decision is how do we split these programs up into different sections? The two methods that we need to know about are segmentation and paging, sometimes called pagination. I'll usually just refer to it as paging though. Most modern operating systems use a combination of both paging and segmentation in their memory management. Of course, this is a very abstract overview. In real life, things get a lot more messy and a lot more complicated. Let's take a closer look at segmentation. So memory is split into segments. Segments are logical divisions that hold complete sections of programs, such as modules or routines. These segments are not of fixed size. They are as large as necessary to hold the process. And this is what we use for RAM on our computers. Paging, to contrast with segmentation, we divide memory into pages. Each page is a fixed size division of memory, often several kilobytes. Pages are physical divisions rather than logical. The operating system then uses a page table to keep track of where the pages are stored. This means all the pages of a process don't have to be stored contiguously. And paging is what we use for virtual memory. So let's take a look at virtual memory in a bit more detail, because you'll often get a question on that in the exam. RAM is significantly more expensive than secondary storage, whether we're talking about hard disk drives or solid-state drives. A computer system will often have hundreds of times more secondary storage than RAM. So, for example, my own system at home, I think, has 16 gigabytes of RAM, and I've probably got round about 1.5 terabytes, not very good writing there, 1.5 terabytes of secondary storage. So you can see there's a big difference there. When a system is running low on physical memory, by that I mean RAM, it is able to use an area of the hard disk or other secondary storage as virtual memory. When the operating system believes that a page of data is not likely to be needed in the near future, it can be moved from RAM to virtual memory. Then when the page is needed at a later point, it can be moved back into physical memory. So this is a kind of key idea here, this idea of constantly switching these pages from RAM into the secondary storage in virtual memory and back again. So the idea is if you need to access the data that's stored in virtual memory, you move it back into RAM. It has to go into RAM before it can go back to the CPU. But if you've got some information, some data that's in the RAM, a page of data that isn't going to be needed in the near future, you can move that into virtual memory and keep it in the secondary storage, and that frees up more memory in RAM for running applications and data. Now this process is slower than keeping everything in physical memory, so we don't want to use it too often. If the RAM is full, the operating system can end up moving pages back and forth between physical and virtual memory too often. And this can significantly slow the system down and can be referred to as disk thrashing. So that's when the disk is constantly being used because virtual memory is constantly being used. We're swapping pages between physical memory and virtual memory all the time. In this situation, adding more RAM will speed up your computer because then it doesn't have to keep going back to the secondary storage for data, which significantly can slow down the process if we're using it too much. So for this, we need to know why we use memory management on a computer, why it's an important function of the operating system. And then we need to know about segmentation and paging, what they're used for, how they're different. And you need to be able to go into a little bit more detail on virtual memory to make sure you can describe how it works, why it's used, and problems with it. Hope you have a good time with your studies. I will see you in the next video.